Hello, everyone. Let's continue with our discussion regarding open-ended waveguide antenna that we started in the previous lecture. So let me quickly mention something that we said an open-ended waveguide antenna in its fundamental mode, which we said it's called TE10, is essentially has an electric field over the aperture, which look like this. So electric field, of course, goes to zero because this is metal. So electric field tangential to the metal is zero. It has a peak here, and the direction of electric field is parallel to the narrow wall, and this is the bigger wall A. And we mentioned that also the dimension of A and B uh, dictates what is the frequency of operation for this waveguide in its fundamental mode, which is TE10. This is the mode. So now the next question that we raised in the previous lecture was how to calculate the far field pattern of aperture antennas and, for example, this antenna. Then we gave a framework, which is we said we know E tangential over the aperture as a function of X and Y. So if this is X and Y, assuming the aperture is X and Y, you essentially need to know your electric field everywhere, tangential to this. So you don't, for example, need to know the normal component. If you know this, then you can find the 2D Fourier transform of this, which we call Kx and Kf, Kx and Ky. Some books write that with capital F. And then after that, we can calculate far field, electric, and magnetic field. So that was the framework that we talked about, and we're going to actually do that. Let me also remind you, I mentioned that in the previous lecture, but it's also important. Let me remind you that this is one framework. The other framework that we learned in this course is if you know electric current, you can find magnetic vector potential, and then you can find your ENH using this method. And if you have magnetic current, you can find electric vector potential, and then you can find ENH. So in terms of analysis in this course, these are really the three main methods. So always you start from source and you go to effect. So now, what are the sources? So effect is essentially our ENH in the far field. What are our source? Source can be electric current, source can be magnetic current, source can be E over the aperture. And these are related to each other, but we essentially classified them into three ways of approaching antenna analysis. So whenever I give you a source and I ask you for the effect, this is essentially you choose one of them to get here. If I give you J, you use this method here. If I give you M, you use this method here. If I give you E over the aperture, you start with this. So we go from source of the energy to the effect. So that's what we have in the antenna analysis. So now we need to start with an example and to make sure that we understand this. So let's consider that we have an open-ended waveguide antenna like this, and we know the electric field over its aperture. So now I'm gonna remove this stuff from here, and I'm gonna just have my coordinates here again, X, Y, and I'm assuming that this is my waveguide, and I'm also assuming that I know E, which is E naught cos pi xa in the direction of y hat. And if you remember, this point was x equal a divided by 2. This point was x equal minus a divided by 2. Of course, the total length here is a. The total length here is b. And so this is what I know, and the electric field over the aperture of this is like that. We mentioned in the previous lecture that we call this cosine taper. So that's exactly my open-ended waveguide antenna here. Now, we have that, but then let's start with finding the first step, which is F, the Fourier transform. So if you look at your note from previous lecture, you see that fkxky is going to be integral from minus infinity to plus infinity e tangential xy e to the power of j kxx plus kyy dx dy. So this is what we have in our transformation to go from E to F. So, and we mentioned that this is essentially 2D Fourier transform. The reason it's 2D is that you have one dimension along X, one dimension along Y, of course. Now, the first observation here, that's going to be a little bit confusing if you pay attention to here. To calculate this integral, what you need to know what is electric field from minus infinity to plus infinity in both dimensions. But if I have an antenna like this, what you know is electric field over this aperture. But this essentially tells you that, for example, you need to know what is electric field on this plane, 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 and so on. So you essentially need to know the electric field not only here, but also here, because it's minus infinity to plus infinity. And that's a problem for us. So to have an exact calculation, I'm going to make an assumption, and then later on, we're going to talk more about this assumption. So the assumption that I'm going to make is that this open-ended waveguide antenna is actually open through, imagine you have a metallic plane. So this is a metallic plane, and then this is the aperture of the waveguide, and the waveguide is coming from the back. So something like that. So maybe this is also the coaxial cable that's feeding the waveguide. So this feeds the waveguide, and then it come here, and this is a perfect electric conductor, PEC, and this goes to plus infinity, minus infinity, plus infinity, minus infinity. And you know that plus infinity, minus infinity, these things mean electrically large with respect to wavelengths. If you are large with respect to wavelengths, then you are essentially, it goes to infinity. So this aperture, we are assuming this is an aperture, and then we have a big metallic plane that's in parallel with the aperture. Let me bring something and show it to you exactly what I mean. Okay, so what I meant by this structure is that, look, this is my open-ended waveguide. Now, this is a copper tape. So imagine this is like a big PEC plane, so it's metallic. So imagine if I have this open-ended waveguide here, and I have the aperture through the hole in this metallic plane. So now, if I bring that almost flush to the surface of the aperture, now the situation is interesting, because now we know the electric field over the aperture of the open-ended waveguide, and also we know the electric field on this entire plane, because this is metal, so the tangential field over metal is 0. And how big is this metal really depends on the wavelengths. Now, if this open-ended waveguide works at 10 gigahertz, so it's the wavelength is 3 centimeters. So if you're looking at 10 lambda, for example, 10 lambda is only 30 centimeters. So you can have a reasonably sized PEC plane and assume that this is big. So the structure that I'm plotting here is exactly this thing here. And the advantage of that is that on this PEC plane or metallic plane, or in this case copper tape, you know that E tangential is exactly 0. And you just pretend that everywhere it's going to be 0 except on the aperture. So if I do that, then again, you know that on the aperture, the electric field is non-zero. It's in fact cosine taper, but outside it, it's going to be 0. And remember, electric field on the surface of the PEC, just the tangential component is zero, but you could have a normal component on the surface of a metal, but tangential is zero. But that's all we care, because that's E tangential. Now, based on this becomes very beautiful, because then you can just remove this minus infinity to plus infinity, because everywhere outside the aperture is zero, and just say integral over aperture, because outside is going to be zero. So that's what we're going to be integrating in our work. So this is essentially the structure that we are performing the analysis in this case. So let's perform our integration and see what we have. So let's put everything here. Okay, I have my f. I have my f kx ky is going to be equal to integral E over aperture is going to be E naught cos pi x divided by A. I have a y hat here. Perhaps it's better for me to have the y hat outside. And then I'm going to have e to the power of j kxx plus kyy dx dy. So now I know that my x is from minus a divided by 2 to plus a divided by 2. That's the range of x, because now I'm only concerned with the aperture. My range of y is from minus b divided by 2 to plus b divided by 2 here. So that's going to be essentially what I need to integrate. Okay, so to integrate that, let's start perhaps with the easiest one, which is integration over y, because I don't have this cosine here. So let's integrate over y first. So what I'm going to have, it's going to be y hat e naught, and then I'll have integral of x from minus a divided by 2, a divided by 2, cos pi x a e to the power of j k x x. These are related to x. And then I'm going to have one integral from minus b divided by 2 to plus b divided by 2 only for j k y dy. And then the whole thing is going to be integrated with respect to x. So I'm going to first integrate the y component. Now, integration with respect to y component, which is this term here, is relatively easy, because you know that e to the integral of e to the power of ax is 1 divided by a e to the power of ax. So we know that, so therefore we can easily do that. But in this case, your a is jky. I mean, a wasn't a good example because you may confuse it with the dimension, but you know what I mean here. So let's do this for that. So it's going to be 1 divided by jky e to the power of jkyy from b divided by 2 to minus b divided by 2, because that's the limit of my integration. Based on that, I can write this as 1 divided by jky e to the power of jky b divided by 2 minus e to the power of minus jky b divided by 2. That's what I have. So that's what I have, and I can still simplify it, and let's see how we can do that. You also remember that sine of theta is e to the power of j theta minus j theta divided by 2j. That's the expression of sine in terms of exponential. Now, if you look at here, you immediately identify the numerator of this. So numerator is going to be 2j times sine theta. The same thing here, I can write that as 1jky, which is that. And instead of that, I'm going to write 2j sine ky b divided by 2. That's going to be my expression. And you see that j and j cancel, and you get something like this, that you have sine ky b divided by 2 here, and you can also write ky b divided by 2, and you multiply by b here, and you exactly get the same thing. Remember, this 2 goes to the numerator, becomes this 2. This ky that you have here is this ky. I just multiplied the denominator by b and the numerator by b to have this structure. And the reason I want to have this structure instead of this one, which seems easier, is that I can convert it to sinc function. And you perhaps remember from your math that sinc of x is defined as sine of x divided by x. That's the definition of a sinc function. And to just remind you, this is the sinc function, which is the Fourier transform of a rectangular pulse. So that's my sinc function. Therefore, I can write that as b sinc of ky b divided by 2. So you see, I started with performing this integration, and I went all the way and I arrived at sinc function. So I can now remove everything here, and I can just write that as b times sinc ky b divided by 2. So that's my sinc function for here. So this is my sinc function. Now, does that make sense conceptually or not? This is something that we need to answer at this point. After that, we go to this step. Does this make sense conceptually or not? We can easily see that that makes perfect sense, because look at your electric field distribution over the aperture of a open-ended waveguide antenna. This is your x, this is y. So now, if you move along y, what do you see if you move along y? So first of all, here was PEC, here was PEC. So when you move from here, tangential electric field is 0 over the PEC. So let me bring that here again. So what I'm saying is, for us to start moving in the y direction, move from here. Tangential field is 0, 0, 0, 0, 0, nothing. We arrive at the open-ended waveguide antenna. And then all of a sudden we have electric field. And if we are moving in the y direction, this electric field doesn't change. This is like it doesn't have any taper in the y direction. So it's 0. All of a sudden you have an electric field over the aperture, which doesn't change in the y direction. And then you finish you arrive at the other side of the aperture, and then again electric field becomes 0, because now you are on the PEC. So now if I plot this field over the aperture, this is what we're going to have. Starting from PEC, nothing, and then all of a sudden an electric field, and then again nothing. This is what we're going to get if we move along y. Nothing, all of a sudden electric field, then nothing. Now, if I ask you, what is this function from courses related to signal processing, you know that this is rect function. This is a pulse function. Sometimes we write it like that. So the Fourier transform of this function is a sinc. So if you take the Fourier transform of this, you get sinc. And that's exactly what happened in the y direction. We had a pulse, rectangular pulse, and then the Fourier transform of it is going to be our famous sinc function that we have. And that's our sinc function exactly because of that. So conceptually, this calculation makes sense. So let's consider this, and let's move on with calculating this part. So I know this part. Now I want to calculate the x. So I'm just going to calculate this one because this one doesn't depend on x anyway. It's just think of ky b divided by 2. So to calculate this, I'm going to remove this stuff from here. And I'm just going to write minus a divided by 2, a divided by 2 cos pi x divided by a, e to the power of j kx x dx. Now, there are multiple ways of calculating this. One way to do that is to write cos in terms of exponential. That's just one way. And if I want to remind you, let me remind you by this, that cos of theta is e to the power of j theta plus minus theta divided by 2. That's your cos function. So then you can write this as minus a divided by 2 plus a divided by 2 e to the power of j pi xa plus minus j pi xa divided by 2 e to the power of jkxx dx. So this is what I have. The beauty of this approach is that you can combine these e and then perform an easy integration. For example, you can now write this as half integral of e to the power of j pi a plus kx x, and then plus e, and then you're going to have minus j pi a minus kx x dx, and you go from minus a divided by 2 to a divided by 2. Let me make sure I have it correct. Pi a here, kx there, and then minus pi a here, then again kx over there. So then we can easily calculate that this is going to become half, and this becomes 1 divided by j pi a plus kx times e to the power of j pi a plus kx, now xa divided by 2 minus e to the power of j pi a plus kx minus a divided by 2. So now this is the calculation of the first term of the integral. The second of the integral would be similar to this, and it's going to be plus half. Now this is going to go here, and that would be minus j pi a minus kx. Then you're going to have e to the power of minus j pi a minus kx evaluated at a divided by 2 minus e to the power of minus j pi a minus kx evaluated at minus a divided by 2. And then you close it. That would be the evaluation of this integral. Now, if we look at this integral, we see something that we can take advantage of that. So in particular, I want you, for example, to consider this term. This term is e to the power of j pi a plus kx times a divided by 2, which is, if I start multiplying it, it's going to be e to the power of j pi divided by 2 times e to the power of j kx a divided by 2. So that's what we're going to have. And this term is equal to j. And the reason is, if you use Euler equation, where it says e to the power of j theta is cos theta plus j sine theta, substitute theta with 90, you get cos of 90, which is 0, plus j sine of 90, which is 1. So you end up with just a j. So that's what we're going to use here. So let me remove that. So if I use that, then this part would be a j. So what remains, so I can just get rid of this, and that turns into a j here. And then what remains is ejkxa divided by 2. So ejkxa divided by 2. That would be the one that I have. And here I have the same thing, but this time instead of j to the 90, it becomes j minus 90 because I have a negative sign. So this contribution here, it's going to be, it's going to result in minus j for me. So I can just remove that. So, I mean, let me repeat it in case you missed it. It's pi a plus kx times minus a divided by 2. That's going to be minus j pi divided by 2 minus jkx a divided by 2. So this term here, so this is multiplication. This term here, that's minus j. So I can just have minus j here. And if I have minus j here, this negative would be plus. So that's going to be a plus j. And then what remains is just this kx times that, which I have it here, minus jkx a divided by 2. So minus jkx a divided by 2. So that's my simplification here. And now I'll get to this, and I'm going to do exactly the same thing. So here I have minus j pi a times a divided by 2. That's going to give me something like that. So that's going to be minus j for me. So here I can have it minus j. So there is a minus j here. And then what remains is the positive kxa divided by 2, similar to that. So this becomes minus j e to the power of jkx a divided by 2. And here I have negative times negative positive. So I'm going to have a positive j. There is a negative here. So it's already negative. And for kx, I'm going to get negative because I have 3 negative here. So this is going to be negative j e to the power of minus jkx a divided by 2. So that's the other term that I have. Now, if you factor j from here, this j is going to cancel this j. So this is going to cancel this j. And this negative j, if you factor it, is going to cancel this negative j. So then I'm going to have this situation that I'm going to have, I'm going to remove this. I'm going to remove this. I'm going to remove this. And when you look at this expression here, you see this structure, e to the power of j theta plus e to the power of minus j theta. You see, this is exactly that. And based on what I explained earlier, this is 2 cos theta. So I can just remove that and write 2 cos kxa divided by 2. So that's what I have. And the same thing here, if I get rid of these, I'm going to have plus half and then 1 pi a minus kx that I already had. And here, I'm going to have 2 cos kxa divided by 2. So I'm going to have 2 cos kxa divided by 2. That would be what I have. And then I can start simplifying this. So let me remove here and write it as, so this 2, by the way, can cancel this 2, and I factor cos kx a divided by 2, and then I'm going to have 1 pi a plus kx plus 1 pi a minus kx, and that's going to give me pi cos kx a divided by 2, and then pi a minus kx plus pi a plus kx divided by pi 2 a2 minus kx squared. And that's going to give me 2 pi divided by a cos kx a divided by 2, and then I'm going to have 1 divided by pi 2 a2 minus kx squared. Let me check if I have this correctly from my notes. So this seems correct. The only thing that I haven't done to be consistent with my note is to multiply both. So if I multiply both numerators and denominator here by a square, so that's going to be pi square. So that's going to be pi square. You're going to get another a square here, and this kx square would be minus kxa, the whole thing square. If you multiply numerator and denominator by a square, then you have a here. That's going to be cancelled, one of the a there. So this would be gone, and this becomes 2 pi like that. And then you can combine this 2 pi by the a here, and that's going to be 2 pi a that. So, and that's exactly what I have in my note. So based on this, we also have this integral. So now I can combine them to have the final answer. And that, therefore, the final answer would be this. So remember, this was the Fourier transform, kx, ky. And that I can just write it as kx, ky equal to, so y hat, we had the direction y hat, E naught, and then we had B here, so, and we have an A here, so I'm going to multiply these together, AB, and then I'm going to have 2 pi, and then I think this was pi square, if I'm not mistaken. Yes, that was pi square coming from here. Pi square minus kx a square. Then sinc function, sinc of ky b divided by 2 times this cos kx a divided by 2. So that essentially becomes my 2D Fourier transform of the aperture field that I calculated. Now, before continuing with this, let me tell you something here. The same way that I explained why this should be sync, because you essentially, if this is your open-ended waveguide, if you move along the y, what you see is nothing, because its E tangential is 0 over the surface of PEC, and then you see a pulse, and then nothing again. So that makes a pulse, and then you have sync function exactly here. But now if you move along x direction, what do you see? Again, when you are here, you are on the surface of the PEC, you don't see anything. But then what you see is a half cosine. And then you see again nothing. So here you see a pulse, that's why you have sync function. But in the x direction, you see a half cosine, because the electric field over the aperture is essentially cosine tapered, half cosine. So now, if you wanna find this thing here, this is essentially the Fourier transform of this cosine. And if you want to find that based on Fourier methods that we know, you can think of it as a cosine function. So you can think of it as a cosine function. So this is a cosine function. So this is a cosine function. This is a one cosine function, and then you have a rect function like this. So if you multiply them, if you multiply a rect function by a cosine function, you get this, because then this rect is only going to choose this part. So if you want to find the Fourier transform of this, is the same as saying find the Fourier transform of this multiplied by that. Then Fourier transform of multiplication would be convolution. So it would be Fourier transform of this convolved with this. And if you follow that, you should get exactly the same response based on that method as well. But remember, this is essentially a cosine multiplied by a rect, which we calculated here. So that's essentially our calculation of a Fourier transform with justification why we should get these things. And the reason I wrote A, B here is to emphasize that this is the area, physical area of the aperture, because we know that this is A, this is B. So I wrote it in a way that we actually see the area of our aperture. Okay, now what we have here is that we have the Fourier transform. Let me just remind you that this was our procedure here. So we said we know the E tangential over the aperture. So we know E tangential over the aperture, and then we find this F that we found, and then we're going to go to far field E and H. So now, we've achieved this. Now we need to go to this step. So that would be what I'm going to do right now. But before that, I need to write the equation that I wrote in the previous lecture. So the equation is far field E at an observation point, let's say r theta and phi, is equal to jk or jk naught, whatever you prefer to call it, e to the power of minus jkr 2 pi r. Again, I want to emphasize here that this factor here is for the spherical wavefront that you have, and then multiplied by theta hat fx cos phi plus fy sine phi plus phi hat component times cos theta minus fx sine phi plus fy cos phi. So let me double check this. Theta hat fx cos phi, fy sine phi. I have phi hat cos theta minus fx sine phi plus fy cos phi. Now, something you realize here is that plus r hat times 0, because if you are in the far field and the radiation in the r hat direction, E has to be perpendicular to r hat. So there would be no r hat component, as we stated in the previous lecture. Now, the other thing you see here is that because for this open-ended waveguide antenna, this electric field was along y direction, we only have fy. So in fact, whatever remains after y hat is fy. So if you, for example, if I identify this for you, this is essentially your fy. We don't have any fx. So based on that, we can perform some simplification that this would be gone. This was fx, and this would be gone as well. So maybe I can write it now more compact. So that would be theta hat fy sine phi, then plus phi hat cos theta fy cos phi. So this would be my electric field for this antenna. So the only thing you need to do is to get this fy. Of course, this y hat, you just ignore it. This is your fy. You just take this fy and substitute it here, and that there you can have your electric field in the far field. So, and I emphasize here, this is for the far field. This approach that we explained is for the far field here. So you take just Fy, and this is Fy, and you just substitute it over there. So then what would be our H? So H in the far field would be R hat cross E divided by eta. So what's going to happen is that I'm going to have J k e to the power of minus jkr 2 pi r, the same way that I have here, but that's going to be divided by eta because of that. Then what would be r hat cross theta hat? So this is our, what we have, right? So r hat cross theta hat is going to give me phi hat. So that would be phi hat Fy sine phi plus, now r hat cross phi hat, but now you're going in the reverse direction, so it's going to be minus theta hat. So here I'm going to have minus theta hat cos theta Fy cos phi. So now, as you see, you have both your E and H component in the far field based on this mechanism. So really, if you want to compute this, the main computation is to calculate this 2D Fourier transform. Here we did it based on mathematics, but also you can do it based on the use of, for example, computer programs to perform this 2D Fourier transform. So that's one thing here. Now let's even simplify that even more. So to simplify it even more, this time, this would be my question for you, that I would say I'm interested in far field E, but I'm interested in far field E only in the E plane. So you see, this is in a three-dimensional space, but now I'm limiting myself to the E plane, and I'm asking you what would be far field. Now, then you need to ask yourself, what is the E plane cut here? So to understand the E plane cut, remember that this antenna, the main beam of this antenna, maximum radiation is along the Z. So this is the direction of maximum radiation, and the polarization of electric field is in Y. So you have Z for the direction of maximum radiation, you have electric field over Y, therefore E plane is YZ plane. So that would be your E plane. So E plane becomes YZ plane. So that would be your E plane. So now, what is YZ plane? Because this is in a spherical coordinate, you need to somehow represent YZ plane on the spherical coordinate. So remember, if you are on the YZ, always this phi in a spherical coordinate is 90 degrees, because phi starts from X, goes in this way. So if you are on this plane, phi is 90 degrees. So when you are on YZ, phi would be 90 degrees. So what you can do is to substitute for phi equal 90 here to get your E plane. So let me remove this, and I'm saying E plane YZ, that's equal to phi equal 90 in a spherical coordinate. So I would say E in the far field is going to be, I'm going to just say equal jk e to the power of minus jkr 2 pi r theta hat Fy sine phi is sine of 91, and then cos of 90 0. So that term completely gone, and I'll get theta hat Fy. So this is a very beautiful expression here, because it tells you that your electric field in the far field, in the E plane, is directly related. This is actually, when you go to the far field at certain distance r, this is a constant here for you, is directly related to the Fourier transform. So essentially, if you want to know your far field in the E plane cut, just take the Fourier transform of your aperture, and you have your far field electric field. So now if you just substitute Fy here, you have your electric field. And remember, if I'm on the E plane, which is this plane, I could also be on the Z axis. So this is Z axis, and let's assume this is the far field. Now, this is my electric field. Now, electric field might look like this is in Y direction here, and then you might say Y, Puyan has it as theta direction. So this is something that we need to, I mean, maybe if we go to three-dimensional, we can easily see that, hopefully. So if you are in the YZ plane, so this is my YZ plane, so this portion. Now look at theta hat. These are your theta hat. So if you look at your theta hat, when you are on the YZ plane, then in the beginning, when you are on the Z axis, the direction of theta hat is the same as Y hat. So if I'm on the Z axis, this is the electric field. So this is Y hat in Cartesian coordinate, but in a spherical coordinate, that's essentially your theta hat too, because you're going this way. So I just want to say that in this case, theta hat would be same as Y hat. So this would be the electric field on the E plane, and it's gonna do that and then come here. And when it comes here, look at theta hat. Theta hat becomes like this. So theta hat, in fact, becomes minus z hat when it arrives here, because z hat would be this. Theta hat in this case becomes minus z hat. And so it does that, and it comes here, and you see it's going to be perpendicular to the whiteboard, which is fine, because when it gets perpendicular to the whiteboard, remember, outside the aperture, we had PEC. So on PEC, you cannot have tangential field components. Let me bring this for you here. So imagine this was my antenna as we discussed. Now, if this is the electric field here on the E plane, this is my E plane. If this is the electric field, now it becomes perpendicular to this copper plane, which is fine, because you can have normal components to this, but you cannot have tangential components. Now, this is and if you want to see exactly what would be the electric field on the PEC, remember, on the aperture, so let me have that again here. So if you want to know what is the electric field over the PEC, remember, this aperture is XY plane. So when you are on the XY plane, is the same thing as saying theta is equal to 90, because theta starts from Z axis, and then if you go 90, you are on the XY plane. So XY plane is theta equal 90. So if I want to see what is electric field on the plane, on the whiteboard, I need to substitute theta equal 90. Now, if we do that, let's see what's going to happen. So what would be my Fy? Fy, maybe it's best if I start with calculating Kx. Kx is K sine theta cos phi, as we explained in the previous lecture. Now, I said I want to be on E plane. So phi is 90. So this is a cos of 90. This is essentially 0. So Kx is 0. Ky is K sine theta sine phi. Now, phi is 90. This is 1. And theta, if I want to be on the aperture plane, I need to substitute theta equal 90, because xy plane is theta equal 90. So this becomes on the xy plane and on the E plane at the same time. This E plane means phi equal 90, xy plane means theta equal 90. That brings me exactly on the y axis. That's going to be just k. So if my kx is 0, what's going to happen to my fy? I'm going to have E naught AB. This is 0, so that's going to be 2 pi divided by pi 2. Now, cos of kx becomes 0, cos of 0 becomes 1, and then I'm going to have sinc of kb divided by 2. That's going to be my sinc function here. There, I'm going to have sinc kb divided by 2, and the direction is, of course, theta hat. So you're going to have some electric field on this, on the E plane, over the aperture. But then remember, the direction is theta hat, so that's going to be perpendicular to the PEC plane. So that's not going to create any problem. Remember, tangential field over metal is supposed to be 0. So that's for your E plane.